Good morning to everyone. MT8791 Embedded System Design, final year, 7th semester, Mechatronics, Regulation 2017. So, Unit 1 Introduction to Embedded System Design. So, already we have seen three parts in this Unit 1. So, up to this, we have completed that processor technology and IC technology. So, in this video, we are going to see about the design technology. Okay. So the design technology involves the manner in which we convert our concept of desired system functionality into an implementation. So we must not only design the implementation to optimize the design metrics, we must do so quickly. So as described as earlier, the designer must be able to produce a large number of transistors every year to keep the pace of IT technology. So improve the design technology to enhance the productivity has been the focus of the hardware and software design communities for decades. So to understand the improve the design process, we must first understand the variations of top-down design process have become popular in the past design. So the designer refines the system through several abstraction levels. So at the system level, the designer describes the desired functionality in some languages, often natural language like English, but preferably executable language like C. Okay. So in this previous slide, we have so many levels of abstraction when we go for an embedded system design. So first one is compilation. Obviously, we are going to design one product in the sense we have to program. So in that program, we have to check whether the error is inside that error is coming or not. So we have to compile. The next one is the library. If you want to design one product in the sense, we have to add that libraries and intellectual properties. The next one is test and verification. If you cross this, uh, uh, if you cross these steps in the sense, we are going to the final implementation. Okay. So in that system level specification, behavioral specifications, and there are register transfer level specifications and logic level specification. These are the abstraction levels of that particular design. Okay, so if we are by finding any error in the sense in the logic specifications in the sense, again we have to check in the RTL specifications. So when we go for this system level specifications, then behavioral specification, if you're facing any behavioral specifications in the sense, again we have to check the system specifications. Likewise, the abstraction levels of this embedded system design will based on the compilation and the libraries and test and verifications. Okay, so in this slide, we shall call this system specifications. The designer refines the specification by distributing a portions of it among chosen processors. So the designer refines these specifications into register transfer specifications by converting the behavioral of a general purpose processor assembly code to by converting behavior of single purpose processor, the connection of register transfer components and the state machine. The designer then refines the register transfer level specifications of a single purpose processors into logic specification consist of a Boolean equations. So finally, the designer refines the remaining specifications into an implementation consists of machine code for general purpose processors and a gate level netlist in a single purpose processor. So definitely we are going on RTL level specifications in the sense at last by the netlist comparison we have specified what are the components inside, what are the interconnections, how it working, how it's typed, how it the functionality, how much time it takes to complete that process by means of this netlist analysis. Okay. So this diagram, this image is represent in 1960s. They have used assembler linkers. The 60s and 70s we have used the compilers. So these are used to understand like a C program to machine understandable languages. Okay, so assembly level language into machine level language into by the assemblers. Assembly level languages compiled into that machine level language in the 1960s to 1970s. The next one is 1970s to 1980s. We have used the logic synthesis. We have because used the logic gates for implementation of this ASIC and VLSI processors. The next one is 1980s. We use RTL level specifications like register transfer level specifications in 1960s and 1990s. The next one is 1990s. We have used the behavioral synthesis to analyze all the languages and a variety of languages we have used like a VHDL and HDL. and embedded C. So this implementation will reflect on your whole embedded system processes. Okay. The next one is compilation. So compilation synthesis lets a designer specify desired functionality in an abstract manner and automatically generate a lower level implementation details, describe the system at a high abstraction levels, can improve the productivity by reducing the amount of details, often in order to magnitude that a design must be specific. So a detailed logic synthesis tool converts a Boolean expression into logic gates. Okay. So in that compilation, we are using that logic synthesis tool to convert a Boolean expression. If you are using that any Boolean expression to design one functionality in the sense, it will be converted into a logic gate. So that functionality we can see in that netlist by means of this register transfer synthesis tool. So this register transfer synthesis tool will convert a finite state machines and register transfer into data path of RT components and controller of Boolean equations. Okay. The third point, the behavioral synthesis tool will convert a sequential program into finite state machines and register transfers. So likewise, a software compiler converts a sequence program to assembly code, which convert essentially the register transfer level code. So finally, a synthesis tool convert an abstraction level specifications into set of sequential program and general purpose and single purpose processes. Okay, so these are all the various levels of compilation and the synthesis tool. So in this slide, they have explained about the previous slides in 1960s and 1970s, what they are used in the register transfer level synthesis tool and behavioral synthesis tool. So these type of operations will be performed by this type of technology. After that, finally, we have used the synthesis tool to form to the implementation of the particular processes. Okay. The next one is libraries. We involve a reuse of pre-existing implementations. Using a library existing implementation can improve the productivity if a time takes to find, acquire, integrate, and test a library item is less than designing the item of oneself. The logic level library may consist of layouts for gates and cells. Okay. So an RT levels library may consist of layouts. So like registers, multiplexers, decoders, functional units. So in the RT level specifications, we have variety of components. So a behavioral level library may consist of commonly used components such as a compression, components, interfaces, display controllers. So these are the various components when we go for this behavioral specifications. The next one is system level integration has got a great level of library rather than the components. ICs they have now must also available form called codes that we can implement under just one portion of library. So the behavioral level libraries of ICs, libraries of codes has prompted use of the term called intellectual property to emphasize the fact that uh, the fact that the course in existing in a soft form that must be protected from copy. So finally, a system level library must consist of complete system in solving particular problems such as interconnection processes with accompanying the operating system and implement to interface to the real-time applications. Okay, so in that we have seen the various behavioral specifications, RTL level specifications, what are the components, and why we go for these intellectual properties. So that's why we have explained in this tools slides. The last phase is test and verification. So ensuring the functionality is correct. Okay. So such assurance can prevent the time-consuming debugging at a low level abstraction. Okay. If we reach that expecting outcome in the sense, definitely the entire component is working. We need not to test any inside the component in between the lower level abstractions layers. Okay. So the simulation is the most common method of testing functionality correctly. So at the logic level, gate level, simulators provide output of timing various waveforms. Obviously, if you are designing an embedded system in the sense, by means of the testing tools like the simulators and the emulators, we can use that what are the particular device functionality by means of some CRO or something, some emulated devices, we can predict the simulation behavior of the particular embedded system design. Likewise, a general purpose processor, he simulates, he executes the machine code at RT level. The hardware description language simulators execute RT level descriptions and provide output waveform given input waveform. Okay. So at the behavioral level, HTL simulates a sequential program and the co-simulator connect the HTL and the general purpose processors simulators to enable hardware and software co-verification. A model simulator simulates the initial system specifications using an abstract computation model independent of any processor technology to verify the correctness and the completeness of the specifications. Okay. So a model checkers can verify certain properties of specifications, such as ensuring the certain simulation simultaneous conditions never occur or that system does not deadlock. Okay, so at that particular deadline, the components which is inside the processor, it should work. So for that, we are using the simulations, and by means of that HDL simulations and VHDL simulations, we can use the verification of the particular devices. Okay. So that's I'm completing the design technology. So in this design technology, we have concentrated about the test and verification and the libraries and the compilations. Okay. So in the following slides, in the next class, we are going to see about the hardware software co-design. Okay. Thank you.